So another set of questions in which we focus not on the functional group, but on the type of reaction, in this case addition reactions. You know, two types of addition reactions: electrophilic addition, which involves carbon-carbon multiple bonds, and nucleophilic addition, which involves carbon-oxygen double bonds. I'm also going to throw in elimination for fun. Because I'm focusing on addition reactions and the type of questions, I'm splitting into easy questions, mechanistic questions, and harder questions. What you'll see is that the nucleophilic and the electrophilic are a little bit mixed up, not hugely mixed up, but you'll do an electrophilic and then you'll do a nucleophilic and so on. And this is just to emphasize the commonality of the reactions as well as some of their differences. So anyway, leaping straight in. Question 1 from 2018, which asks about alkyne, ethyne. We didn't actually study ethynes and alkynes, but you did study alkenes, and so you're supposed to recognize here that you have a carbon-carbon multiple bond bristling with those pi electrons, which can quite easily do addition reactions. So you take an alkyne and add hydrogen to it, you make an alkene, which of course you do know reacts with hydrogen if there's some left to make an alkane. And this is of course an addition reaction. One type of addition process that's very important at A-level is that of addition polymerization. Relatively straightforward process, I think, to going from the alkene to the monomer to the repeat units. And there is our alkene in this case, pent-2-ene, 1, 2, 3, 4, 5 carbons, double bond starting at 2. Let's make it a little bit prettier so we can see the groups attached to the double bond. It's the double bond that is all important. So whether there's a 1 carbon group, the methyl, or 2 carbons after the double bond, that's carbon 4 and 5. Who really cares? What's important is there's the double bond with the bits attached to it. It didn't specify E or Z pent-2-ene. I happen to think the E's are just prettier to draw, so that's the one I've done. Anyway, to now turn this into a repeat unit, we lose one of the bonds in the double bond and replace it by a bond on each of the carbons, going away from the molecules. The one on the red goes that way, one on the orange goes that way, and then just put them together like this. So there is the red and the orange of one, red and the orange of another one. You can see the H and the methyls of the red ones, the ethyl and the H of the orange ones. Same type of question. There is the monomer below showing 2 repeat units. So again, let's make it look pretty. So we got this C double bond with the groups on it. This group here, a bit nasty to draw, especially on a computer. Carbon goes to the C, which has an H and OH and a CH3 on it. Again, to draw the repeat units, just lose one of the bonds in the double bond and stick on an extra bond to the left and to the right and put them together like that. So on the red carbon, the hydrogen, and then this OH, CH, CH3 group, and then on the orange carbon, the chlorine and the hydrogens. Section of polymer shown. Draw the structural formula of the monomer used to make this polymer. Now it's a little bit nasty here because if we look at the red carbons, I've taken the liberty of really colouring things in, by the way. Look at the red carbons, no problem, methyl on top, H on the bottom. But the orange ones, they've drawn it so that you've got the chlorine on top and hydrogen on the bottom for one, hydrogen on top, chlorine on the bottom for the other one. Nothing dire there, but what we should do is we should actually just make things a little bit more consistent. So let's first of all rotate that second orange one. So now this is what that polymer looks like. And now we can readily see by cleaving the bond there, by adding in the double bonds, you've got methyl hydrogen on the red one, chlorine hydrogen on the orange one in that order. No reason why I had to pick putting the chlorines on top and the hydrogens on bottom for the orange one. So if I rotate it the other way, we get this picture here again. Cut it there and stick in the double bond between the 2 carbons, and here we see the methyl hydrogen on top still, but now the hydrogen and the chlorine have been switched. State type of polymerization involved, well, it's an addition polymerization, already talked about that. And now 1 repeat unit of this polymer when the 2-fluoro-but-2-ene, so there it is drawn out pretty again. So there's the double bond, it's on the 2, there's carbon 1, carbon 2, carbon 3, carbon 4, fluorine on carbon 2 again. drawn it as the E. Well, actually, in this case, I've drawn it as the Z because, of course, fluorine has a higher ranking than the methyl group, but it just looks prettier when you kind of do it like that, I think. But anyway, so usual thing, remove the double bonds, stick in the extra bonds there. So that's the red one, methyl fluorine. That's the orange one, hydrogen methyl. Complete the equation below, which shows the reaction of benzaldehyde with hydrogen cyanide. Well, of course, this is an addition. The cyanide being the negative goes on the slightly positive carbon. The hydrogen being the positive goes on the slightly negative oxygen. And you get that little addition there again. Cn on the carbon, H on the oxygen. Formula of the nucleophile that takes part in the reaction shown in part A. Well, the nucleophile is the bit that likes positive, so it's the bit that's negative, and so it's the Cn minus that attacks the carbon first. And in later questions, we'll redo, of course, the mechanism of that. So, displayed formula for the aromatic compound formed when anethol reacts with hydrobromic acid. Well, here's anethol. We're going to react that with HBr. Okay, it's going to be an addition across this carbon-carbon double bond. The question is, of course, does the hydrogen go on the red one, so the bromine goes on the orange one, or does the hydrogen go on the orange one, so that the bromine goes on the red one? And of course, what you will find is standard Markovnikov addition, right? And that is that the more electronegative atom, which is definitively bromine, goes on the more substituted carbon, which in this case is the orange one. Again, although we'll do the mechanism of this later, if you remember, this goes through a carbocation so that the hydrogen goes on the less substituted carbon and even the more substituted carbon with the positive charge. Indeed, this goes through not just a more substituted carbocation, but a so-called benzylic carbocation, which has super duper resonance stability because you can have one of the pi electrons here comes out here. So this is the double bond, and then you spread out that positive charge around the ring. 2-chlorobutane heated with sodium hydroxide in ethanol. So this is now going to be an elimination reaction. We get 3 different organic products. Okay, so there is our 2-chlorobutane. You've got the chlorine there that's definitely going to go, but then we're also going to lose a hydrogen that is on the beta carbon. So we got these pink ones on what I will call carbon 1 for no reason at all other than that's carbon 1, so that's carbon 2 with the chlorine on it. Then carbon 3, because that's got a methyl group on it, the other 2 hydrogens are different from each other. So I've got a blue and a red. So first of all, let us remove one of the pinky ones. Okay, and so then there's that carbon 1, carbon 2 there. Chlorine went off carbon 2, the hydrogen went off carbon 1, and what's left over here is the hydrogen and then CH2, CH3, no ambiguity there. If we remove the blue one now, well, now we've got the methyl group here, carbon 1, that goes on to carbon 2. Carbon 2's lost the chlorine, so it's got the hydrogen there. Now, if I lose the hydrogen, the blue hydrogen off carbon 3, then the methyl will be on top and the hydrogen will be on the bottom. Or if I lose the red one now of carbon 3, now the methyl moves to the bottom, the hydrogen will be on top. So therefore you have the 3 possible ones. Which one would be more stable, even though it doesn't ask it? This one, because the more substituted alkenes are more stable. Here you've got 1 non-hydrogen group. Here you've got 2 non-hydrogen, 2 non-hydrogen. Between the 2 non-hydrogens, the trans isomer, as this is the E isomer, is better than the cis. Very similar question. Bromoethane can be converted to ethene. So there's bromoethane, turn it into ethene. What are we going to do? Well, we are eliminating. So we're going to use sodium hydroxide in ethanol, and that will lose the HBr, giving us this. Type of reaction, well, I've just said it's elimination. And 2-bromobutane. So there's 2-bromobutane. Reacts in a very similar fashion. However, you get 2 alkenes that are structural isomers are formed. Well, here's the 2 bromobutane, and we can lose either pink ones or blue ones. In this case, unlike the last question, we're going to care about structural isomers. Last one, we also worried about the geometric. So structural, we're either losing from carbon 1 or from carbon 3. Lose from carbon 1, we get that species, which is 1,2,3,4,1-butene. Lose from carbon 3, we get this one, which is 2-butene. And of course, the 2-butene, analogously to the last question, can either be E or Z. Ethanol can be produced from many different sources. In industry, most ethanol produced from ethene. Give reagents conditions, you either know or you don't. There's ethene. Effectively add water across the double bond, the OH and the H, giving you ethanol. Industrially, conch, phosphoric acid, nice high temperatures, very high pressures of the ethene. In the lab, you can use conch phosphoric or conch sulfuric, much less foreseen conditions, lower atmospheres, lower temperature, and so not as good a process. Ethanol can be produced from chloroethane in a nucleophilic substitution reaction using aqueous sodium hydroxide. We don't really care about that part because that's a substitution, but we do care about under different conditions, sodium hydroxide can react with chloroethane to produce ethene. So there is chloroethane getting turned into ethanol via the substitution. However, we then react it up with different conditions. The sodium hydroxide can produce 2-ethene right there. And those different conditions are in ethanol instead of in aqueous. And of course, this is an elimination. Okay, so this is part of a much bigger question. We're only worried about the important salient bits for what we want. So ethane reacts with carbon monoxide and present water to produce propenoic acid. This is what we're interested in. There is propenoic acid. So you can see it's 1, 2, 3 carbons. You got an acid on it, and then the ene must be between carbon 2 and carbon 3. So repeating unit, as usual, we'll just place the double bond with a single bond and one each that direction, and then put the polymerization on it with the little brackets and the N. New method to obtain propanate implementation super sugar. This method gives 3-hydroxypropanoic acid right there, which can then be converted to propenoic acid via application of reagent U. Well, how do we essentially dehydrate an alcohol, because this is the alcohol bit, to give us an alkene? And the answer is, in the lab, we're going to use sulfuric acid and a relatively high temperature.